Hello there. Sorry for the delay and the interruption. I finally found a calculator for the rest of the problem, so let's continue. Back then, in the first part, we talked about how we calculate the stress and then how we calculate the strain, transform the strain, and then obtain the stress and transform the stress to the particular orientation we wanted. Now, the key thing here is that if we know there's some limitation on the stress in that direction, what is about allowable pressure in the pressure vessel? Okay, so following last time's discussion, we arrived here at this equation. Okay, so I continue inside the bracket now. I have a 0.75 minus 0.25 multiplied by minus 0.174. Okay. And then this roughly gave me a 0.79 PR over T. Okay, so now I basically have a 0.79. Bring the PR ratio, right? What is R? Sorry, bring the RT over T ratio, right? So what is R? R equal to a 12-inch, T equal to a 0.25. Okay, so this gives me P 0.79 multiplied by 12 by 4, because this is basically 1 over 4. So now I have a basically equation of forces, right? So let me do a simple calculation here real quick. I press on my calculator 0.079 multiplied by 12 multiplied by 4, and that gives me a 37.92, so 37.92 P. Okay, so this is basically a relationship. Let me highlight this portion. This is the relationship between a normal stress along the n direction, okay, in the function of P, as a function of P. Okay, now we said previously the constraint for our case is this has to be smaller than 60 megapascal. 60 megapascal. So my P has to be smaller than 60 divided by 37.92 megapascal. So equal to do a quick calculation, 60 divided by 37.92 arrive at a 1.58 megapascal. Okay, so you notice that to have a pressure on the outside surface of cylinder less than 60 megapascal, my pressure inside the pressure vessel has to be smaller than almost 1.6 megapascal. It's a very small value. All right, so this just tells you that what is important here, R over T ratio, that is to say how thin the shell is. That is very important for design. Okay, very important for design. Okay. All right. With this, we basically conclude the pressure vessel problems. Okay. So I want to show you some variations, right? Some variations you can have based on this type of solutions, right? For instance, so let's just say example number 1. Okay, this is my pressure vessel. Again, let me try my best to draw it right. Okay, now I say now the cylinder was welded with the themes in the angle with the horizontal direction by theta. Okay, and I tell you now the size of the pressure vessel is R, thickness is T, internal pressure is P. I tell you all this, right? Then my question is, if I have a theme like this, and the strength of the weld, of course, all these are weld, okay? All these are welds. Is a certain number, right? Say 50 megapascal. Okay, that's the strength of the weld. What will be allowable pressure? What will be the allowable pressure that I can have in the pressure vessel? Okay, so how to solve this problem? It's essentially the same, isn't it? Essentially the same. So first thing first, I will establish my coordinate system. This is y, this is x. Equivalently, this is L, this is theta, this is theta, right? Actually, let me use a different symbol here. Let's just say this is beta, okay? And let's just say beta equal to 60 degree. Beta equal to 60 degree, okay? So this is to ask you, if this is a beta plane, okay, what will be the normal stress? What will be the normal stress on this plane? Okay, so if this is the case, I'm going to draw a perpendicular line here. Okay, perpendicular line here with respect to the beta line here. And don't forget the right-hand rule, okay? Right-hand rule. So let me draw this right-hand rule right here so we can understand. The right-hand rule goes like this. So if you point out your thumb direction, okay, and this is your normal direction, okay, rotate by a 90 degree, you have the T direction, okay? So this is the right-hand rule. Okay, now we're going to apply this right-hand rule to our setting here. So this is the thumb direction. And rotate by 90 degree. Actually, rotate by the 90 degree, I have basically a... Sorry, okay? Let me draw it clearly. Let me redraw it, okay? So when I say my thumb direction is actually pointing outward to us, isn't it? Outward to us. By the way, this is outward out of the plane to us. This is out of the plane opposite to us. Okay, so I'm looking at a thumb direction towards us, and then this is my N, so I'm gonna rotate by a 90 degree and get my T. Okay, so this is my new coordinate system, and you remember that when we talk about stress transformation, if I want to transform stresses from XY to a NT direction, I always use the theta, and that is coming from X towards N, right? Coming from X towards N in a counterclockwise direction, okay? So here now, in my case, theta N equal to a 90, this is 90, plus here, and this is 60, 30, so this is 60, okay, plus is 60, so I had 150 degrees, okay, 150 degrees. So what you're seeing here is I already start thinking about stress transformation because I know it is easy. Okay, let me write it down so you know this. It is, so first, key point, right, key point. First, this is a combination of pressure vessel and stress transformation. First thing first, okay? Second, okay? Need to link P to sigma xy and then to sigma nt. Okay, So that is basically the thought process of solving this type of problem. So first of all, we identify it is a combination pressure vessel stress transformation. Then we're trying to connect pressure to stress in XY plane. Or if you want to say, you can call it L theta plane, and then to the NT plane. Okay, so let's take a look at overview again, okay? All right, so with this thought process, we can start solving the problem. Okay? Now here we go. We can start by first step, find out the P to sigma X and sigma Y, okay? So from existing equation, we know that sigma X or sigma L longitudinal stress equal to PR over 2T. Okay, if you don't remember this, let's go all the way back here, L, PR over 2T. Okay, then theta or Y, PR over T. Okay, so I have now sigma Y, PR over T. Okay. And then I'm going to use the stress transformation equation that is sigma n equal to what? Equal to half of sigma x plus y, half of sigma x minus y cosine 2 theta, tau xy sine 2 theta. And I already know for this case, tau xy equal to 0, right? Tau xy equal to 0, right? No share, right? So immediately I arrive at sigma x plus sigma y divided by 2, okay? Sigma x plus sigma y divided by 2 here, plus sign, sigma x minus sigma y divided by 2, cosine 2 theta. Okay, now be careful. Here has to be theta n 2 theta, okay? 2 theta, okay? And theta n equal to 150 degrees. Okay, 150 degrees. So now sigma n equal to half PR over T, 1 plus half, okay, plus half PR over T, half minus 1. Okay, sorry. If I follow the sequence precisely, this should be half plus 1. Okay, and cosine 300. Okay, cosine 300. Now, so sigma n now equal to PR over 2T. Okay, here 1.5, here minus 0.5. So here 1, right? So 1.0. Okay, so if it's 1.0, we might as well leave it. Okay, but sorry, I forgot this fellow right here, right? So this is essentially equal to 1.5 minus 0.5 and cosine 300 degrees. All right, so now you can either use calculator to find out cosine 300 degrees, that's what I'm doing right now, or you can actually do this. Cosine 300 degrees basically equal to cosine 2 pi minus 60 degrees. And this equal to cosine 60 degrees equal to a sine 30 degrees equal to a half. Okay, so after this tiny process, I can get sigma n equal to a PR over 2t, 1.5 minus 0.5 multiplied 0.5. Okay, so this is quarter. So this gives me a 1.25. Okay, so sigma n equal to a 4 over 5 multiplied PR over 2t. So 5 PR over 8t. All right. So now I basically have a stress transformation and also connect my sigma n to my p here. And from the problem, I know what I wanted is sigma n equal to 5/8 PR over T has to be smaller than 50 megapascal. So my P has to be smaller than, right? Has to be 80 T divided by R. Okay, 80 T, 5 cancel, 810, 80 T reversely divided by R megapascal. Okay, so this is the type of problem you can have as a variation of the problem we studied before. Okay, all right, example number 2. Same pressure vessel, okay? And the same angle here, but instead of the well, I'm going to put a strain gauge here, and I call it beta equal to 60 degrees. And I'll give you P, R, T, all right? And I will ask you, what about my strain in this n direction? Be careful, okay? I should say strain in the beta direction. Okay, be careful. This is not the strain in perpendicular to the line there. This is directly the strain in the beta direction. Okay, so what you do, right? This is what you do. First, you do the same thing as we did before. X equal to PR. X equal to PR. What is it, right? Take a look if you don't remember it. 2T. You see it? 2T. PR over 2T. Y equal to a PR over T. Okay. Then what you do? Then you use plane stress condition. Plane stress condition. Then sigma x, so epsilon x equal to 1 over E. Of course, E and nu are known. Sigma x minus nu sigma y. Okay. Epsilon y equal to sigma y minus nu sigma x. Gamma xy equal to tau xy divided by g. And of course, we know this is 0, no shear, right? So let's write it out. Epsilon x equal to 1 over E sigma x PR over 2T minus nu PR over T. Okay. So let's get collected form. So PR over E T bracket inside 0.5 minus nu. So that's x, right? So y equal to 1 over E sigma y equal to a PR over T minus nu PR over 2T. So this gives me an 1 over E, so PR over ET again here. Inside though, this 1 minus mu multiplied by 0.5. Okay, so after all this, I have my strain in terms of epsilon x equal to PR over ET 0.5 minus nu, epsilon y equal to a PR over ET 1 minus nu divided by 2. And I know my shear strain is 0. Shear strain is 0. And then you can use a strain transformation. Strain transformation to calculate epsilon beta. How so? So epsilon beta equal to half of epsilon x plus epsilon y plus epsilon x minus epsilon y divided by 2 cosine 2 beta. So epsilon beta equal to half PR over ET bracket inside 0.5 minus mu plus 1 minus half mu, okay, plus PR over ET 0.5 minus nu minus 1 plus nu 2. Now cosine 2 beta, given beta equal to 60, so cosine 120 Again, this, if you want to write it, equal to cosine pi minus 60. Okay, so that basically equal to a cosine. Let me punch in the calculator real quick. So 120. Okay, so I got a minus sine 30. Okay, equal to a minus 0.5. So epsilon beta equal to a half of PR over ET. Okay, 0.5 plus mu, 0.5, I'm just copying things down, minus nu plus 1 minus nu plus 0.5 minus nu minus 1 plus half nu, bracket, don't forget, multiply minus 0.5. Okay, so now I get epsilon beta, copy it down, PR over 2ET here, so collect the terms, half, 1, quarter, right? So it's 0.5 plus 1 minus 0.25 plus 0.5. Okay, then minus nu divided by 2 minus half multiplied by minus half nu. Okay, so epsilon beta equal to PR over 2ET. I'm pretty slow with my algebra, hasn't done it for ages, I'm sorry, okay? So this is 2 this is 1, 2 minus, so 1.75, okay? Here's minus 1 minus half plus a quarter, so this is plus a minus 1 minus 0.5 plus 0.25 nu, okay? Very slowly, I get epsilon beta PR over 2ET, 1.75, here collect the term, minus 1.25 nu. Okay, so that is the strain in the beta direction. Okay. All right, so at this point, you can see, if I want to study a pressure vessel, I can do several variations. But regardless, the common thing that you do for pressure vessel is that one, understand or solve for the longitudinal stress, the hoop stress. B, convert longitudinal stress, hoop stress into an arbitrary N, T, and NT stress. Other ways, I can convert L theta to strain L theta, then convert into NT. Okay, so regardless what you see in the exam, you're basically trying to find out the stress in the longitudinal and the hoop direction. Either convert the stress into the other orientations, or convert the stress to strain first and convert the strain to other orientations. All right, so not too bad. But the problem can get very difficult. The problem can get very difficult when you have combined problems. Okay? All right, so at this point, we're officially done with the pressure vessel. Okay? And thank you for watching. We're going to start the combined loading in the next lecture.